So, good morning, everybody. So, in this lecture, I wish to discuss about the vapor pressure of a fluid. So, this is also one of the important properties of fluid, and where we really use the application of vapor pressure is especially where the pressure changes occurs rapidly, whether it is in the case of a pipeline like venturimeters, or in the case of turbines or pumps where there is a possibility of cavitation due to the pressure drop. So, if we want to understand that, first we should understand what's the property that is responsible for a phenomena leading to the damage of the turbine blades, the damage of the pump blades, and the damage of the pipelines because of a process called cavitation. And we, as civil engineers and mechanical engineers, we need to really see that cavitation does not occur, whether it is in the case of a pipeline, or whether it is in the case of a turbine, or whether it is in the case of a pump. So, if you want to analyze that, first you should know what it is. That's why this lecture is devoted to only to understand what is vapor pressure. So, straight away, I take you to the whiteboard. So, in today's class, let us discuss about vapor pressure. The word vapor pressure itself signifies it is the pressure of vapor. It is the pressure of vapor. Pressure applied by vapor. So, if you understand first, it is the pressure of vapor, pressure applied by vapor. Generally, for example, if you take our the fluid like water, which generally we always look. In the case of water, we see vapors only if its temperature is raised. When the temperature of the liquid is raised by heating, when once it reaches to boiling point of water, you observe vapors coming out of the fluid. But if you see the petrol, you just keep the petrol in just small vessel at room temperature itself and then observe it. The evaporation starts immediately, and you can see the evaporation. In no time, the whole liquid petrol turns into vapors. But on one side, Only if we boil to a temperature of 100 degrees centigrade, we are able to see vapors there in water. Whereas in petrol, if we really raise the, just keep it at room temperature, still we are able to observe. Then you need to think both fluids, if you observe it, why one is behaving like this, one, whereas the other is behaving only when its temperature is raised. That means there is a property, there is an inherent property of the fluid which is responsible for that type of phenomena. And that is what we call it as vapor pressure. All liquids have a tendency to vaporize. But this rate of vaporization is very low in some fluids and high in some fluids or liquids. Just let us understand. You take a closed vessel. This is a closed vessel containing liquid like this. This is all empty space. The pressure here is vacuum pressure. No air inside, right? Now, just what we observe. What we observe is after some time, after maybe 5 minutes or 10 minutes, if you observe it, from this liquid surface, because the liquid consists of only liquid molecules. This is all liquid molecules. So which the molecules which are nearer to the surface, because of their high kinetic energy, they move into this space. So now the molecules in terms of vapors, these are all vapor molecules. These are all liquid molecules. And this surface is free surface. Again, after some time, if you observe, Already here there are like these molecules. So this is all liquid. So on one side, these molecules from the free surface going out. Whereas on the other side, because of here, what will happen is these vapor molecules collide and they lose their kinetic energy, and then they try to move again into the liquid surface. Here we can see three arrows down and five arrows up. The meaning of that to understand is five molecules are leaving from the free surface, three molecules are entering it. Again, you do observe for some more time. All time only, but the container is sealed. Suppose you see this is liquid. And you observe basically from the free surface, this is what we are observing continuously. Molecules are leaving, and here also the molecules are again entering. So at some point of time, this rate of vaporization is equal to rate of condensation. At that time, the pressure, the partial pressure applied by the vapor molecules of the fluid on its own surface is called vapor pressure. And when this occurs, when the rate of vaporization, that means the evaporation, is equal to the condensation. The rate at which the molecules leave the free surface and the rate at which the molecules enter the free surface are equal. Then the pressure applied by these vapor molecules of on its own liquid surface, on its own, here one more word you can add here, on its own liquid surface is called vapor pressure of that particular fluid, vapor pressure of that fluid. Every fluid is having its own vapor pressure. For example, I will give you the values also just for understanding. For example, if you take it water, the vapor pressure at 20 degrees centigrade is, that's what I mean by room notes. For water, it is 2.34 kilonewton per meter square. For example, if you take it for gasoline, at again the same temperature, if you take it, it is 55 kilonewton per meter square. See how many times it is higher. Then next, if you see, for example, mercury, again at same temperature, if you see 0.17 into 10 to the power of minus 3 kilonewton per meter square. Here it is very high compared to water, but compared to this is very low actually, whereas here it is high. The high vapor pressure indicates it is the fluid is volatile, very easy to evaporate, easily at low temperatures also it vaporize. Volatile means easily evaporated, so quickly evaporated. That is what this. Mercury, you take it, its vaporization, vapor pressure is very low. So here this vaporization is in mercury, vaporization is very, very, very low. That is why mercury is used in barometer. Barometer is used to measure atmospheric pressure. Barometer or any pressure measuring devices. So this is why it is being used there, because it won't vaporize quickly even if you are increasing the temperature. Even water, when the boiling occurs, when it is heated up to 100 degrees centigrade, the whole liquid turns into vapors. So naturally it requires 35 degrees, 40 degrees, 45 degrees, then vapors will generate. So that is why, so that means the liquid starts converting into vapors. So here that is why mercury is a very, very low vapor pressure fluid. That's why it is being used in barometers. Then the another thing, normally vapor pressure basically depends on two things. Vapor pressure depends on temperature and pressure. That is important thing. Suppose you see, for example, as the temperature increases, vapor pressure also increases. As the temperature, for example, before going to that, for your understanding sake, I will take water. For example, if you take for water, the temperature versus vapor pressure, if you take it first, at 20 degrees centigrade, the vapor pressure will be approximately 17.5 torr. Torr is again another unit to measure the pressure unit. But my interest is not more, don't concentrate on torr, concentrate on the values actually. As the temperature increased to 25 degrees centigrade by heating it, then the vapor pressure actually has increased to 23.5 torr. And when it increased to 45 degrees centigrade, it has increased to 55 torr. And if it has increased to 60 degrees centigrade, we observe it has gone to 149 torr. And when it increased to 90 degrees centigrade, then actually it has gone up to 529 torr. And if it is increased to 100 degrees centigrade, then it has come to 760 torr. That 760 torr is nothing but P atmosphere. So that means when the temperature is raised, when the temperature is raised up to 100 degrees centigrade, the vapor pressure of the fluid, vapor pressure of water is equal to atmospheric pressure. That is why when you keep it in a container, you don't see any vapors. But if you heat it such that the vapor pressure is increased to the atmospheric pressure, that means the pressure around surrounding it. For the example, if you take this vessel, open vessel, water is there here. If it is 20 degrees centigrade, you see here what is the pressure actually? It is atmospheric pressure. The pressure here is, if you take it at the surface, it is atmospheric. Just below the thing, what is the vapor pressure of this is? This is vapor pressure of fluid. Because of this vapor pressure of fluid, which is basically at 20 degrees centigrade, 17.5 torr, naturally it immediately you cannot see anything coming out, because this is P atmosphere here is greater than P vapor pressure. When can you observe boiling? Boiling is observed only when atmospheric pressure is equal to, or when better wording is, when vapor pressure is equal to atmospheric pressure. That means when the pressure is increased to from vapor pressure to atmospheric pressure, automatically the vapors start. So that is why you can achieve boiling of a liquid. That means boiling of a liquid means converting the liquid into vapors by raising the temperature. That is what I wish to clearly tell you here. Or what is the other way? For example, the second one, the first parameter, temperature, I told. The second parameter is what actually? The pressure. If the pressure is reduced to the vapor pressure of fluid, then also vaporization starts. That is, you take it. For example, water. In the case of water, if you see, suppose now you have sealed the water in a container. So this is water. The difference you understand. It is actually at 20 degrees centigrade only. Now what you have done here, it is what? Empty space. Empty space means what? Here actually what is the pressure? It is vacuum pressure. Right? If this is vacuum pressure, You understand? And here basically the pressure is the vapor pressure of fluid. Vapor pressure is greater than vacuum pressure. Then what happens from here, where the pressure is low here, pressure is high here, vapor pressure is a little bit high, vacuum is zero. So when it is that, because of that, the vapor molecules from the free surface enter into this space. Otherwise, how they enter? This is how they enter. But after some time, what will happen? Here it is no more vacuum pressure. Here vapor molecules are there. That means the pressure is increasing. And when the pressure is increasing here, and when the pressure actually here is equal to the vapor pressure of the fluid, when the pressure here is equal to vapor pressure of the fluid, then that means when that is possible, when rate of vaporization is equal to rate of condensation. At that time, at that time also boiling starts. At that time also the liquid changes into vapor. So that means if the pressure at any point in the flow, if you reduce it to vapor pressure of that fluid, then it vaporization starts. Then the liquid turns into vapors. We come across this in case of pipe flow, where we want to find out the discharge in the case of pipes, the flow rate in the case of pipes. Suppose this is a pipe of diameter d. So what I connect in order to find out the discharge in this pipe, we connect it to a meter called as venturi meter. So this is pipe, this is also pipe, right? This device from here to here is called as venturi meter. And what for this venturi meter is used? To measure the rate of flow, flow rate. Flow, how much is the flow taking place in the pipe per second? Flow rate in the pipe, to measure it we use. So what is the principle we use? Is we try to contract the flow section. What we have done? Contract the flow section. When we contract the flow section, pressure is reduced. When pressure is reduced, there is a possibility that here the pressure may be equal to or less than vapor pressure of the flowing fluid. Then what we observe actually, if suppose I take this is the device, just I enlarged it. So in this region, pressure is reduced. So here the liquid, if suppose you take water, it is flowing. This water converts into vapors, bubbles. These bubbles, when reaches to this region, for example, this is the bubble. So because of high pressure here, these bubbles collapse. When these bubbles collapse, they apply some force on this pipe boundary. So when they apply force on this pipe boundary, here cavities are formed. Pipe or venturimeter damages. This is one. So here formation of vapor bubbles, collapse of vapor bubbles, applying pressure on the boundary leads to formation of cavities. Same is the case in turbines, pumps at the blades. That means turbine blades, pump blades. The blades damage because of three things. Number one, formation of vapor bubbles. What is the second thing actually? Collapse of vapor bubbles. What is the thing? Application of high impact pressure. Leads to these three, leads to formation of cavities on the surface. On the surface of venturimeter inside turbine blades, pump blades, and all this gets damaged. And this phenomena of, once again, formation of vapor bubbles, collapse of vapor bubbles, the application of high impact pressure due to collapse of bubbles leading to formation of cavities, thereby surfaces damages. This is called cavitation. We should avoid cavitation at any point in the flow. The only way that you can avoid cavitation is observing the pressure and ensuring that the pressure never drops to below vapor pressure of that fluid. Whichever fluid is flowing, that fluid, if you take, fine. If it is water, vapor pressure of water. If it is another fluid, that you should take it. But when I deal only with as in civil engineering, we deal most of the things with water. So that's why when I say always fluid or liquid, you please understand it is water unless I specifically mention another liquids or name fluids name. So kindly remember. So always the pressure should, if the pressure at any point in the flow, if it is less than vapor pressure, then cavitation occurs. So now you understand why we are studying this particular property of fluid vapor pressure. One, two things. Very, very low vapor pressure fluid, we are using it in pressure measuring devices. That is mercury. Other water, whatever we are using to avoid the cavitation phenomena. For these reasons, we have studied this particular topic. So this is the application. So here we stop actually this lecture.
Like, share and subscribe. Hit the bell icon for more updates.